What if I told you that right now, as you watch this, an invisible web stretches across the entire cosmos, a hidden architecture so vast it defies comprehension? Picture the universe not as empty space between stars, but as a living tapestry woven together by threads we can't see, touch, or even fully understand. These are the filaments of dark matter, the silent scaffolding of existence itself. They're the reason galaxies don't fly apart, the cosmic glue binding everything from the smallest dwarf galaxies to the largest superclusters. And yet, despite holding the universe together, dark matter remains one of science's greatest mysteries, a ghostly presence we've only begun to trace. Think about the last time you looked up at the night sky. Those pinpricks of light, they're not floating in isolation. Each one is anchored by forces far stranger than gravity alone. Dark matter filaments stretching millions of light years like celestial spider silk connect galaxies in a web more intricate than any neural network. Without them, the universe as we know it would unravel. Stars would drift into the void, galaxies would scatter like leaves in a storm. But here's the most mind-bending part: we're only seeing a fraction of the picture. Over 80% of the universe's matter is invisible, undetectable by telescopes, hiding in plain sight. So how do we even know it's there? The answer lies in the way galaxies move, the way light bends around empty space, the way the cosmos behaves in ways that defy every visible clue. Scientists have spent decades piecing together this puzzle, and what they've uncovered is nothing short of revolutionary. Dark matter isn't just some background player, it's the architect of the largest structures in existence. It shapes where galaxies form, how they cluster, even the fate of the universe itself. And today, we're going to pull back the curtain on these cosmic threads, exploring how they work, why they matter, and what they reveal about the hidden forces scripting the story of everything. Buckle up, this isn't just a journey through space, it's a voyage into the unseen foundations of reality. Picture the universe not as a vast, empty darkness dotted with galaxies, but as something far more alive, a sprawling, dynamic network pulsing with invisible energy. The cosmic web is its backbone, a labyrinth of dark matter filaments crisscrossing the cosmos like threads in a three-dimensional tapestry. These aren't just passive strings in space, they're bustling highways where matter rushes along gravitational currents, clumping together to birth galaxies at their intersections. It's eerily similar to how neurons connect in the human brain, thin filaments branching outward with dense clusters at their nodes. Just as synapses fire with electrical signals, these cosmic pathways hum with the movement of gas, dust, and stars, funneled by the gravitational pull of unseen dark matter. Or think of it like the root system of a giant tree, drawing nutrients toward key hubs where life can flourish. The universe builds its grandest structures not randomly, but along these hidden routes, as if following a blueprint we've only just begun to decode. Here's what's wild: without this web, galaxies would be scattered like lonely islands in an endless ocean. Instead, they cling to the filaments like pearls on a string, drawn into superclusters where thousands of galaxies gather in shimmering metropolises. Scientists have mapped these tendrils by watching how galaxies move, like tracing wind patterns by seeing which way leaves drift. Even light bends around these invisible threads, revealing their presence through distortions called gravitational lensing. But the most astonishing part, this web isn't static. It's growing, stretching, evolving with the universe itself. As dark matter's gravity tugs on ordinary matter, it sculpts the cosmos over billions of years, determining where stars ignite and where vast voids remain desolate. We're literally witnessing the universe under construction, with dark matter as its unseen architect. Here's something that might rearrange how you see reality: the stars, planets, and glowing gas clouds we call the universe. They're just the tip of the cosmic iceberg. For every speck of visible matter, every galaxy, every nebula, every atom you've ever touched, there's 5 times more dark matter silently shaping the cosmos. Imagine holding a snow globe where the glitter represents everything we can see. Now picture the liquid inside as invisible, heavier than all that glitter combined, dictating how it swirls and settles. That's the universe we actually live in. Dark matter isn't just hiding in the shadows, it's the main event. While visible matter makes up a mere 5% of the cosmos, dark matter claims 27%, weaving its gravitational influence through every corner of space. The remaining 68%, that's dark energy, an even more mysterious force pushing the universe apart. But today, we're focusing on dark matter's hidden hand, how its filaments don't just coexist with visible matter, they command it. Think of it like this: if galaxies were cars, dark matter would be the roads, bridges, and traffic signals determining where they go and how they cluster. Here's where it gets counterintuitive. We've always assumed that what we see dictates what happens, but in space, the opposite is true. When astronomers first noticed galaxies spinning faster than their visible mass could explain, it was like watching a merry-go-round whirling impossibly fast with no one pushing it. The math demanded something extra, an unseen force gripping those stars in place. That's how dark matter was discovered, not by catching it directly, but by seeing its gravitational signature everywhere, like fingerprints on a cosmic crime scene. These filaments of dark matter don't just linger passively, they're cosmic architects. Take the Great Wall of Galaxies, a structure over 500 million light-years long. Visible matter didn't build that. It's dark matter's gravitational skeleton that drew gas and stars into those colossal patterns, like iron filings pulled into the shape of a magnet's field. Even now, as you hear these words, dark matter's tendrils are funneling gas into new galaxies along preordained routes, like invisible rivers guiding fish to spawning grounds. So why can't we detect this stuff directly? Dark matter doesn't emit, absorb, or reflect light. It interacts only through gravity, slipping through our detectors like a ghost through walls. But its dominance raises a humbling thought. The universe we see through telescopes, it's just the decoration draped over a framework we're only beginning to map. Every time astronomers measure the bend of starlight around seemingly empty space or simulate the universe's growth on supercomputers, they're sketching the contours of the invisible majority. And that sketch is rewriting our place in the cosmos. We're not just made of star stuff, we're riding the currents of something far stranger. The universe plays a trick of light so clever it reveals its own secrets, like cosmic sleight of hand where emptiness bends the heavens. Gravitational lensing is our window into this illusion, the closest thing we have to X-ray goggles for seeing dark matter's hidden architecture. Here's how it works. When light from a distant galaxy travels toward us, it doesn't always move in a straight line. If its path grazes a dark matter filament, the filament's immense gravity, though invisible, acts like a lens in space, warping the light's trajectory. The result, the galaxy behind it appears stretched, duplicated, or magnified, as if viewed through a funhouse mirror made of pure gravity. This isn't just theoretical. Astronomers have captured eerie arcs of light in deep-field telescope images, entire galaxies twisted into smears and rings around seemingly nothing. Those distortions are cosmic breadcrumbs, tracing the mass of dark matter filaments too faint to see otherwise. It's like mapping a mountain range by watching how wind currents bend around it. Only here, the wind is starlight, and the mountains are filaments with the mass of 100 trillion suns. The more extreme the bending, the denser the hidden structure. Some of the most striking examples come from galaxy clusters like Abell 1689, where light from background galaxies is warped into long, luminous streaks, Einstein's rings, painting a bullseye around the cluster's dark matter heart. By reverse engineering these distortions, scientists reconstruct the filament's shape and weight, pixel by pixel. It's forensic astronomy, solving for the invisible by measuring its shadow. But the real breakthrough isn't just seeing these filaments, it's realizing how they channel the universe's growth. gas and galaxies slide along them like water down a gutter, pooling at intersections to form galactic megacities. Without lensing, we'd never know these highways existed. Now, projects like the Euclid Space Telescope are creating 3D maps of this hidden network, revealing how dark matter's ropes stitch the cosmos together. Each warped image is a clue, whispering where the universe hides its missing mass and how it sculpted everything we call home. To truly grasp how dark matter filaments sculpt the universe, we need to step inside the most powerful digital laboratories ever built, cosmic simulations running on supercomputers. These aren't just fancy animations, they're staggeringly precise recreations of the universe's entire history, tracing how tiny ripples after the Big Bang grew into the vast web we see today. Take the Illustris TNG project, a virtual cosmos so detailed it simulates billions of years of gravitational tug-of-war across a cube of space over 1 billion light-years wide. Here's the magic: by programming just 2 key ingredients, dark matter's gravity and the physics of ordinary matter, these simulations predict structures that match our real-world telescope images with eerie accuracy. Watching these models unfold is like speeding up time on the ultimate cosmic construction site. Early on, dark matter condenses into delicate threads like dew forming on a spider web. As gravity amplifies slight density variations, these threads thicken into highways, funneling gas into swirling knots where galaxies ignite. The simulations reveal something profound. Dark matter doesn't just guide galaxy formation, it orchestrates it. Galaxies align along filaments like beads on a string, while voids remain empty because dark matter's gravitational tides swept them clean. What's mind-blowing is how these digital universes solve real cosmic mysteries. For decades, astronomers puzzled over why galaxies spin at certain speeds or cluster in specific ways. The simulations show it's dark matter's hidden scaffolding that sets the rules, like an invisible hand arranging celestial dominoes. Even more impressive, when researchers tweak the simulation's dark matter recipe, say, making it more sticky or faster moving, the resulting galaxies look nothing like reality. It's a cosmic Goldilocks test. Only certain dark matter properties produce the universe we recognize, narrowing down what this mysterious substance could be. The most humbling insight comes from comparing these models to sky surveys. The same filamentary patterns appear in both, proving these aren't digital artifacts but fundamental cosmic blueprints. Supercomputers are essentially time machines, letting us rewind the universe to watch dark matter's first threads emerge, then fast forward to see how they'll evolve billions of years from now. As these simulations grow sharper, they're not just mirroring reality, they're becoming our roadmap to the unseen forces that built everything. At the crossroads of the cosmic web, where dark matter filaments twist and converge, you'll find the universe's grandest metropolises, galaxy clusters. These colossal gatherings aren't random accidents. They're the gravitational anchors of the cosmos, the nodal points where the web's invisible threads pull thousands of galaxies together in shimmering, slow-motion collisions. Picture a massive traffic roundabout where highways meet, except instead of cars, it's galaxies, spirals, ellipticals, dwarfs, all orbiting a common center of gravity dictated by dark matter's hidden hand. What makes these clusters so special is their role as cosmic warehouses. They're where the universe stockpiles its matter, trapping galaxies in gravitational wells so deep that escape is nearly impossible. The Virgo cluster, our local supercluster's beating heart, holds over 1,000 galaxies in a space just 7 million light-years across. That's like cramming all the stars from here to Andromeda into a volume smaller than the gap between us. But here's the twist: the galaxies themselves are just the glitter on the surface. Up to 90% of a cluster's mass comes from dark matter, woven into a vast, diffuse halo that cradles the entire structure. The dynamics inside these clusters reveal dark matter's fingerprints everywhere. Galaxies orbit at speeds that would send them flying into the void if only visible matter were present. Hot gas between galaxies so energetic it glows in X-rays fills the space like a cosmic furnace, held in place by dark matter's gravitational embrace. Even stranger, when clusters collide, as in the famous bullet cluster, the visible gas smashes together and slows down, while the dark matter, detected by its gravitational lensing effect, sails right through like a ghost passing through walls. This eerie separation proves dark matter doesn't interact like normal stuff. It's playing by different rules entirely. Zoom out far enough and you'll see these clusters aren't isolated islands. They string together along filaments like pearls on an invisible necklace, forming superclusters hundreds of millions of light years long. The Laniakea supercluster, home to our Milky Way, resembles a feathery cosmic tendril with the great attractor at its core, a gravitational focal point pulling thousands of galaxies toward it along dark matter's rivers. This hierarchy reveals the universe's organizing principle. Filaments build clusters, clusters build superclusters, all scaffolded by the unseen architecture we're only beginning to map. So why do galaxies flock to these nodes? It's all about gravitational real estate. Where filaments intersect, dark matter's density peaks, creating wells so deep they become cosmic sinkholes. Gas streaming along filaments gets compressed, triggering furious star formation in galaxies lucky enough to be near the junction. Over billions of years, smaller groups merge like droplets of mercury, growing the cluster through a relentless game of gravitational Pac-Man. The result, a self-reinforcing cycle where the rich get richer and the voids between grow emptier, a cosmic Matthew effect written in dark matter's ink. Yet for all their grandeur, these clusters are also cosmic graveyards. The galaxies within them are often red and dead, their star-forming gas stripped away by the cluster's violent environment. It's a stark reminder that the web giveth and the web taketh away. The same filaments that deliver galaxies to the cluster's feast also doom them to a slow, quiet fade. But even in death, they tell us something profound. By studying how galaxies behave in these extreme environments, how they rotate, collide, and fade, we're deciphering dark matter's playbook, one galactic interaction at a time. Between the galaxies, in what seems like empty darkness, rivers of fire flow silently through the cosmos, not made of water, but of gas so hot it could vaporize planets. These are the intergalactic highways, thin tendrils of ionized plasma racing along dark matter filaments at millions of degrees, invisible to the naked eye but glowing fiercely in X-ray telescopes. They're the universe's hidden fuel lines, carrying enough raw material to birth entire generations of stars, and without them, galaxies would starve. Here's how it works. As dark matter's gravity sculpts the cosmic web, it doesn't just guide galaxies, it also funnels gas into the filaments like a cosmic gutter system. Picture a network of pipes feeding a city's water supply, except these pipes stretch hundreds of millions of light years, and the water is superheated hydrogen and helium. When this gas slams into galaxies parked at filament intersections, it triggers fireworks. The gas cools, condenses, and ignites into stars, replenishing galaxies that would otherwise burn through their fuel and fade. Astronomers first spotted these rivers of fire by their faint X-ray glow. In clusters like the Perseus-Pisces supercluster, telescopes detected vast streams of million-degree gas tracing the exact paths predicted by dark matter models, like smoke revealing invisible wind currents. The gas doesn't move randomly, it follows the gravitational grooves carved by dark matter, as predictable as water flowing downhill. Some filaments, like the one connecting the Able 2224 and Coma clusters, are so dense with gas they shine like neon signs in the X-ray spectrum, outlining the web's hidden skeleton. But the real proof lies in the galaxies themselves. Take spiral galaxies near filament junctions. Their star-forming regions often align with the direction of incoming gas streams, like flowers tilting toward rain. Satellite galaxies, too, tend to cluster along these inflow paths, hitching rides on the gas like leaves caught in a current. even more telling. When astronomers compare young, star-bursting galaxies to quiet ones, the difference often comes down to location. Galaxies gorging on filament-fed gas shine blue-hot with newborn stars, while those cut off from the web's supply fade to red and dim. This gas isn't just passive cargo, it's a cosmic record-keeper. By analyzing its composition, scientists can trace where it's been. Heavy elements like oxygen and iron, forged in supernova, get swept into the filaments, creating an element-rich slurry that eventually seeds new stars and planets. We're literally made of atoms that once surfed these dark matter highways, delivered to our corner of the universe by gravity's invisible hand, the most mind-bending part. These rivers of fire aren't just relics of the past, they're still shaping the universe today. Right now, gas is pouring into the Milky Way from the so-called local ribbon of cold clouds, a filamentary structure in our galactic neighborhood. It's a gentle drizzle compared to the deluge's feeding clusters, but it's enough to keep our galaxy's star factories humming. Meanwhile, in the distant universe, telescopes have caught galaxies drinking from gas streams like deer at a creek, their star formation rates spiking as the fresh fuel arrives. So why does all this matter? Because these filaments don't just hide dark matter, they're the universe's circulatory system, distributing the ingredients for stars, planets, and life itself. Every time we map a new gas stream, we're not just proving dark matter exists, we're tracing the routes that built us. The cosmos isn't a collection of isolated islands. It's a living, breathing network connected by rivers of fire we're only beginning to see. Somewhere in the depths of space, a cosmic siren calls, an invisible force so powerful it's dragging our entire galaxy toward it at over 600 kilometers per second. Astronomers call it the Great Attractor, and for decades, its true nature remained one of the universe's most frustrating puzzles. Hidden behind the thick dust of the Milky Way's galactic plane, this gravitational anomaly appears to anchor thousands of galaxies in our cosmic neighborhood, all streaming toward it like moths to a flame. But here's the kicker: the visible matter we can detect there, the galaxies and gas clouds, simply doesn't account for the sheer strength of its pull. The answer might lie in the ghostly architecture we've been exploring, dark matter filaments on a scale so vast they redefine enormous. Simulations suggest the Great Attractor isn't just a single dense knot of matter, but the junction where multiple cosmic web filaments converge, creating a gravitational well deep enough to tug on galaxies millions of light-years away. Picture standing at the base of Niagara Falls, feeling the mist from its torrent, except instead of water, it's an unseen river of dark matter, channeling galaxies toward a point we're still struggling to map. What makes this region so perplexing isn't just its power, it's how it challenges our place in the cosmos. Our Milky Way, along with Andromeda and dozens of smaller galaxies, forms part of the Laniakea supercluster, a feathery structure 500 million light-years wide. The Great Attractor sits at Laniakea's heart, acting as the focal point where dark matter's gravitational currents meet. But here's where it gets wild: this isn't even the end of the journey. Recent observations reveal something even larger beyond it: the Shapley supercluster, a megalopolis of galaxies whose gravity may be amplifying the attractor's pull, like a cosmic tug-of-war where we're caught in the middle. Scientists piecing this together face a challenge straight out of a detective novel. Dust clouds in our own galaxy block direct views of the Great Attractor's core, forcing astronomers to study it indirectly, like listening to a concert through a wall. Infrared and radio telescopes have pierced some of the veil, revealing unusual galaxy concentrations like the Norma cluster, which packs the mass of several thousand Milky Ways into a relatively small space. Yet even that only accounts for a fraction of the observed pull. The rest, almost certainly dark matter woven into filaments thicker and denser than any we've mapped nearby, their gravity amplified by the sheer scale of their convergence. This mystery underscores a humbling truth: we're not just floating through space, we're surfing gravitational currents sculpted by invisible hands. every second, those filaments adjust our galaxy's trajectory ever so slightly, setting a course that won't just shape our future, but reveals the hidden mechanics of the universe itself. The great attractor isn't pulling us toward darkness, it's pulling back the curtain on the darkest, most dominant force in existence. While the filaments of dark matter stitch the cosmos together with their dense gravitational threads, the universe holds another equally profound secret: vast deserts of near-nothingness so enormous they could swallow thousands of galaxies without a trace. These are cosmic voids, the shadow counterparts to the web's luminous strands, and they're not just empty spaces. They're dynamic players in the grand ballet of the universe, sculpting the paths of galaxies and stretching the fabric of reality itself. Imagine walking through a city where towering skyscrapers cluster along a few main streets, but between them lie sprawling parks so wide you could lose entire neighborhoods in them. That's the cosmic web: filaments as the dense avenues, voids as the staggering blanks. What's startling is the scale. The Boötes void, one of the first discovered, spans a staggering 330 million light-years. If you placed our Milky Way at its center, you'd need to travel the distance to Andromeda 2.5 million light-years, over 100 times before encountering another galaxy. Yet even this emptiness holds clues. The rare galaxies found inside voids behave strangely, spinning slower and forming fewer stars than their web-bound cousins, like isolated towns cut off from trade routes. Their very loneliness makes them cosmic experiments, showing what happens when galaxies grow up deprived of the filaments nourishing gas streams. But here's the twist: voids aren't passive holes. They're expanding. As dark matter's gravity pulls matter into filaments, it evacuates these regions like a cosmic vacuum pump, creating low-pressure zones that repel rather than attract. This isn't just absence, it's anti-gravity in action. The emptier a void grows, the more it pushes nearby galaxies away, accelerating them toward filamentary walls like marbles rolling downhill. In some cases, galaxies near void edges even stretch into elongated shapes, their stars tugged in opposing directions by the void's push and the filament's pull. The real magic lies in how voids and filaments collaborate. Just as valleys define mountains, voids outline the web's structure. Astronomers actually map filaments by tracing the spherical voids between them, like reconstructing a building's framework by studying the shapes of its empty rooms. Simulations reveal that early quantum fluctuations, tiny wrinkles in spacetime after the Big Bang, determined where voids would form. Regions with slightly less density stretched into today's caverns, while denser patches collapsed into filaments, locking the universe into a foam-like pattern before the first stars even flickered to life. Perhaps most mind-bending is how voids warp time itself. Light passing through these underdense regions loses energy not from darkness, but because space itself expands slightly as it crosses the void. The effect, called integrated Sachs-Wolfe, subtly shifts the cosmic microwave background's temperature, leaving cold spots that mirror void locations like cosmic fingerprints. It's proof that emptiness doesn't mean insignificance. These voids are cosmic sculptors, their gravitational tides steering galaxy clusters into alignment over billions of years, their expansion helping dark energy accelerate the universe's fate. So the next time you hear about the universe's large-scale structure, remember it's not just about where things are, but where they aren't. The void's hollowness carves the web's contours as surely as the filament's density builds it. Together, they're partners in a dance of presence and absence, pushing and pulling the cosmos into the intricate, evolving tapestry we're only beginning to understand. Dark matter defies everything we know about how matter should behave. Unlike atoms and gas clouds which clump together, collide, and radiate energy, eventually collapsing into dense objects like stars and planets, dark matter threads through space like an uncatchable breeze. It forms these vast, stable filaments that persist for billions of years without crumbling under their own gravity. How? The answer lies in its ghostly nature. dark matter doesn't stick to itself or anything else the way ordinary matter does. Picture two scenarios. First, imagine throwing a handful of sand into the air. The grains collide, slow each other down, and eventually fall into a pile. That's normal matter, chaotic and interactive. Now, imagine throwing a handful of smoke. The particles drift right through one another, never colliding, never piling up. That's dark matter. Astronomers call this property weakly interacting. It doesn't emit light, sure, but more crucially, it barely interacts at all, even with itself. When dark matter particles pass each other in a filament, they're like shadows slipping through a sieve. No friction, no collisions, just gravity's silent pull keeping them in formation. This non-stick quality is why filaments stay intact. Normal matter in those same filaments, gas and dust, crashes together, heats up, and eventually condenses into galaxies at the nodes. But the dark matter, it just keeps flowing, maintaining the filament structure like an invisible backbone. Simulations show that if dark matter did interact like regular matter, filaments would have collapsed eons ago, crumpling into dense knots rather than stretching across millions of light years. Here's where it gets weirder. Some theories suggest dark matter might have just enough interaction to explain why filaments aren't perfectly smooth. Think of it like a river with subtle ripples, not enough turbulence to break the current, but enough to create faint variations in density. Certain models propose dark matter particles occasionally scatter off one another, rare as lightning strikes. Others argue that even this is too much and filaments stay pristine because dark matter is utterly frictionless. The debate isn't just academic, it shapes how we search for dark matter in labs deep underground, where scientists hope to catch a fleeting interaction with ordinary atoms. What's fascinating is how this stickiness gap sculpts the universe. Because dark matter doesn't collide, it never slows down. That's why filaments act like cosmic conveyor belts, funneling gas and galaxies toward clusters without losing energy. Meanwhile, normal matter trapped in the web's gravity but prone to collisions piles up where the currents meet, igniting stars and building galaxies. It's a delicate balance. If dark matter interacted more, the web would tangle. If it interacted less, filaments might not have enough cohesion to guide matter at all. The ultimate irony, dark matter's inability to stick, is precisely what lets the universe hold together on the grandest scales. Those filaments aren't just relics, they're highways in constant use. They're non-stick surfaces ensuring galaxies keep moving, clustering, and evolving. And somewhere in that paradox between ghostly indifference and gravitational mastery lies the key to understanding the universe's hidden blueprint. To understand how the cosmic web's filaments first formed, we need to rewind the universe nearly 14 billion years, back to a fraction of a second after the Big Bang. In that searing, chaotic infancy, space wasn't smooth. It rippled with quantum fluctuations, microscopic wrinkles in space-time where some regions held just a bit more energy or density than others. These weren't flaws, they were the universe's primordial seeds, and their faint imprints would one day dictate where galaxies clustered and voids stretched. Inflation, the universe's explosive growth spurt, magnified these quantum quirks from subatomic scales to cosmic proportions. Picture blowing up a balloon with tiny dots drawn on its surface. As the balloon expands, those dots stretch into sprawling patterns. Similarly, inflation stretched those early density variations across light years, creating a faint but indelible blueprint. Where slightly denser patches existed, dark matter would later pool under gravity's pull, knitting itself into filaments. Where patches were emptier, voids would blossom. The universe wasn't just expanding, it was imprinting its future skeleton. This process wasn't random. The patterns we see today, the branching filaments, the honeycomb voids, mirror the mathematical harmonics of those early quantum ripples. Scientists can even reconstruct these fluctuations by analyzing the cosmic microwave background, the afterglow of the Big Bang. Tiny temperature differences in this ancient light, some regions a fraction hotter, others cooler, reveal where matter was initially denser. These hot spots and cold spots align astonishingly well with today's filamentary web, like matching a toddler's fingerprint to the adult it became. Here's the astonishing part: those quantum ripples were unimaginably small. The density variations that seeded galaxy clusters like Virgo or Laniakea, they started as one part in 100,000 differences, a whisper of imbalance in the cosmic noise. Yet gravity's patience turned whispers into shouts. Over eons, dark matter's pull amplified those subtle contrasts, sculpting gas into filaments and stars into galaxies with near mathematical precision. Supercomputer simulations show this elegantly. When you input the initial conditions observed in the cosmic microwave background and let gravity work, the result looks uncannily like today's surveyed universe. But the story doesn't end there. The type of dark matter matters. If dark matter had been warmer, moving faster in the early universe, its filaments would be fuzzier, like ink bleeding on wet paper. Instead, our universe's sharp, thread-like structures suggest cold, dark matter, slow-moving particles that clumped efficiently. It's a cosmic feedback loop. Quantum fluctuations defined where dark matter gathered, and dark matter's behavior determined how those gatherings shaped the visible universe. The most humbling realization: the web structure was inevitable. Given those initial conditions and the laws of physics, the universe could unfold no other way. Every filament, every void, every galaxy racing toward the great attractor, they're all echoes of quantum whispers from a time before time. We're not just mapping dark matter's hidden highways, we're reading the universe's birth certificate, written in the language of gravity and shadow. Scientists have long assumed dark matter filaments would be cold after all. Their ghostly particles barely interact, making it hard to generate heat. But recent observations have shattered that assumption, revealing temperatures so scorching they've sent physicists back to the drawing board. X-ray telescopes like the European Space Agency's XMM Newton have detected filaments between galaxy clusters glowing at millions of degrees hotter than the cores of some stars. This isn't just a minor discrepancy. It's a full-blown cosmic mystery that challenges our fundamental understanding of how dark matter shapes the universe. Take the filament bridging the Abell 339 and Abell 401 clusters. This tendril, stretching over 10 million light-years, radiates X-rays as if it's filled with superheated plasma. Yet, according to conventional models, dark matter alone shouldn't produce this kind of heat. One leading theory suggests ordinary matter, gas accelerated to extreme speeds as it flows along the filament, is crashing into itself like cars in a cosmic traffic jam, creating shock waves that heat the surrounding plasma. But here's the catch: the temperatures measured are up to 10 times higher than these collisions should produce. It's like finding a forest fire where you expected a campfire with no clear source of fuel. Even stranger, some filaments seem to be uniformly hot along their entire length, not just at galaxy-rich nodes where collisions would be most violent. This suggests an unknown energy source is at work, perhaps something intrinsic to dark matter itself. Could dark matter particles occasionally decay or interact in ways we haven't predicted? Might there be hidden physics like dark photons or other exotic particles transferring energy through the cosmic web? The leading theory, called warm dark matter, proposes particles with slightly more kinetic energy than traditional cold models, but even this struggles to explain the observed heat levels. The implications ripple far beyond astrophysics. If filaments are hotter and more dynamic than we thought, they could be accelerating cosmic rays to energies that dwarf anything our particle colliders can produce. Some researchers speculate these sizzling strands might even host exotic states of matter, like quark-gluon plasma from the early universe. The more we study them, the more filaments resemble not just scaffolding, but active, high-energy components of the cosmos' cosmic power lines humming with invisible current. What's clear is this: the universe's hidden framework is far more complex than a simple gravitational mesh. These filaments aren't just cold, inert threads. They're seething with unexplained energy, challenging us to rethink how matter, both seen and unseen, shapes the story of everything. Every new observation peels back another layer, revealing a cosmos where even the darkest corners defy our expectations. For decades, astronomers faced an embarrassing cosmic accounting error. About half the ordinary matter in the universe was simply missing. Atoms, protons, electrons, the building blocks of everything we see, weren't adding up. Based on the universe's elemental composition after the Big Bang, there should have been far more detectable matter than telescopes could find. Galaxies, stars, and gas clouds accounted for barely half the expected total. The rest vanished without a trace, until scientists turned their gaze to the faint, diffuse glow between galaxies, where the cosmic web's filaments revealed their best-kept secret. The missing matter was hiding in plain sight all along, woven into the fabric of the universe itself. This missing matter, what cosmologists call the baryon problem, it isn't exotic like dark matter. It's made of the same protons and neutrons we're familiar with, just fiendishly difficult to detect. Why? Because it's spread incredibly thin, a mist of superheated gas trapped in filaments at temperatures between 100,000 and 10 million degrees. At those extremes, hydrogen atoms get ripped apart into plasma, emitting faint X-rays rather than visible light. It's like trying to spot a wisp of steam in a fog bank, nearly invisible unless you're looking with exactly the right tools. Enter modern X-ray observatories like Chandra and XMM Newton, which finally caught these elusive baryons in the act. By staring for hundreds of hours at filamentary bridges between galaxy clusters, they detected a barely perceptible X-ray haze, the thermal fingerprint of this ultra-diffuse gas. The numbers lined up perfectly. Stacking observations from thousands of filaments revealed enough ordinary matter to close the cosmic ledger. These weren't empty gravitational conduits, they were sprawling reservoirs of plasma, containing up to 50% of the universe's normal matter in a form too ethereal to see with optical telescopes. But here's what's wild: this gas isn't just sitting idle. It's cycling through the cosmic web like blood through capillaries, feeding galaxies at filament junctions. When galaxy clusters collide, simulations show this filament gas gets shock-heated to staggering temperatures, creating swirling currents that channel material into star-forming regions. Some of it even condenses into mysterious, ultra-diffuse galaxies, ghostly, dim structures that float along filaments like cosmic jellyfish. The more we study these intergalactic currents, the clearer it becomes. Filaments aren't just dark matter's domain. They're the universe's plumbing system, circulating the raw ingredients for everything we call home. Yet mysteries remain. Why hasn't this diffuse gas collapsed into galaxies over billions of years? The answer lies in its extreme heat, and low-density particles are too energetic to coalesce under gravity alone, like trying to build a snowman in a sauna. Some theories suggest magnetic fields threading through filaments act as scaffolding, preventing the gas from dissipating entirely. Others propose continuous energy injections from supermassive black holes at cluster centers, like cosmic boilers keeping the plasma bubbling. The true breakthrough came when astronomers matched observations to hydrodynamic simulations. These models showed filaments should contain gas in two phases, a scorching outer layer and a slightly cooler, denser core. Recent detections of faint oxygen emission lines, a tracer of cooler gas, confirmed this prediction, proving filaments aren't monolithic. They're stratified, dynamic ecosystems with their own microclimates, where gas cycles between states like water evaporating and condensing in a vast cosmic weather system. What's humbling is realizing this intergalactic haze isn't just filler. It's the backdrop against which galaxies form and evolve. Every star in every galaxy owes its existence to gas that once flowed along these invisible rivers. Even our own Milky Way likely grew by sipping from local group filaments, as traceable through chemical signatures in ancient stars. The missing baryons were never truly lost, we just needed to learn how to see them. Now, as next-generation telescopes like Athena prepare to map this diffuse web in unprecedented detail, we're not just solving an accounting error, we're uncovering the universe's hidden circulatory system, the lifeblood of the cosmos. At first glance, the universe's largest structures and its smallest particles seem worlds apart, until you notice the eerie similarities. Cosmic filaments, those million light-year threads of dark matter, behave in ways that mirror the spooky connections of quantum entanglement. Both defy our everyday intuition about how objects should interact, revealing a universe far more interconnected than we ever imagined. Imagine two entangled electrons instantaneously influencing each other's spins across vast distances, as if space and time don't apply. Now zoom out. Galaxies separated by unfathomable voids move in sync, tugged by invisible filaments acting like cosmic puppet strings. The scale couldn't be more different, but the underlying theme is the same, a hidden network binding everything together. Here's where the analogy gets thrilling. In quantum mechanics, entangled particles share a single quantum state, so measuring one instantly determines the other, no matter the distance. Filaments pull off a similar trick on a galactic scale. When simulations recreate the universe's growth, they show galaxies moving not as isolated islands, but as nodes in a vast, synchronized web. A galaxy's motion here is subtly echoed by another halfway across the cosmos, linked through the gravitational hum of dark matter. It's as if the universe has its own version of quantum non-locality, where the whole system knows itself instantaneously, not through faster-than-light signals, but through the prearranged geometry of the cosmic web. This isn't just poetic symmetry, it hints at deeper physics. Some theorists speculate that quantum entanglement in the early universe might have seeded the density variations that grew into filaments. Tiny quantum fluctuations stretched to cosmic proportions during inflation could have imprinted entanglement like correlations across space. The result: a universe where the large-scale structure whispers with quantum roots, where the web's threads might trace back to the same primordial interconnectedness that entangles particles today. Of course, the comparison has limits. Quantum entanglement involves instant coordination, while filaments work through gravity's slow, patient pull, but both challenge our sense of separateness. Whether you're observing paired electrons or galaxy clusters, the message is clear. Isolation is an illusion. The universe prefers connection through invisible threads, whether they're woven from dark matter's gravity or quantum mechanics' ghostly handshakes. And that's the real magic. From the tiniest particles to the grandest cosmic structures, the same principle echoes. Nothing truly stands alone. If we could press fast forward on the universe's history, the cosmic web wouldn't look like a static spider's silk. It would pulse and writhe like a living organism. Picture this. In the early universe, dark matter's filaments begin as faint, wispy tendrils, barely denser than their surroundings. Gravity acts like a cosmic sculptor, patiently amplifying those subtle wrinkles over hundreds of millions of years. Gas, drawn like iron to a magnet, starts streaming along these invisible channels, and where currents intersect, galaxies ignite like fireflies flickering to life in a dark forest. Now speed up the clock. Over billions of years, those filaments thicken into sprawling superhighways, their gravitational currents growing stronger as they siphon matter from the voids. Galaxies aren't stationary ornaments, they're travelers hitching rides on these dark matter currents, sliding toward intersections where clusters loom like metropolitan hubs. The Virgo cluster, for instance, didn't always sit at the center of our local supercluster's web. It grew fat by devouring smaller galaxy groups funneled in by filaments, a gravitational predator feasting on cosmic traffic. The most mesmerizing part, filaments aren't just passive roads, they evolve. Some grow straighter as the universe expands, stretching like taffy. others kink and warp when neighboring clusters collide, sending shockwaves rippling through the dark matter network. Zoom out far enough and the entire cosmic web seems to breathe, its filaments flexing as galaxies reel themselves in, drawn by threads we're only beginning to see. And just like commuters changing trains, galaxies can switch filaments. When two massive threads intersect, their gravitational tug of war can fling galaxies onto new trajectories. Our own Milky Way is no exception right now. It's gliding along a filament toward the Andromeda Galaxy, both of them destined to merge in a ballet choreographed by dark matter's unseen hand. Meanwhile, in the distant universe, telescopes catch young galaxies lining up like beads on a filamentary string, their star formation rates spiking as they plunge into denser regions bathed in fresh gas. This time-lapse reveals a universe far more dynamic than we ever imagined, not a frozen sculpture, but a great, slow-motion storm, with galaxies riding dark matter's currents like leaves swirling in a river. And the wildest thought, we're part of the flow too, carried along by filaments whose origins trace back to quantum whispers in the first trillionth of a second of time. The cosmic web isn't just structure, it's the story of everything in motion. For all our talk of dark matter filaments, what if we've been misreading the universe's handwriting? Not every scientist is convinced that invisible particles are the only explanation for the cosmic web structure. Some propose radical alternatives, ideas so bold they rewrite the rules of gravity itself. Take modified Newtonian dynamics or MUND. This theory suggests that instead of hidden matter tugging on galaxies, our understanding of gravity is simply incomplete at cosmic scales. Picture a law of physics that changes its behavior when gravitational pull becomes incredibly faint, like in the outskirts of galaxies where stars rotate inexplicably fast. Mund argues that these odd motions, and even the filamentary structures we see, emerge naturally from tweaking gravity's equations, no dark matter required. Proponents point to certain dwarf galaxies that seem to lack dark matter halos yet still follow Mund predictions. If gravity strengthens differently in low acceleration environments, filaments could form as galaxies naturally align along enhanced gravitational gradients, like iron filings arranging themselves along the unseen field lines of a magnet. But here's the catch: while Mund handles individual galaxies well, it struggles to explain the universe's largest filamentary networks without adding some form of hidden mass back into the mix. The bullet cluster, where visible gas and gravitational lensing maps clearly separate, remains a thorn in Mund's side, evidence that something invisible is bending space-time beyond what modified gravity can easily account for. Then there's the action hypothesis, a twist on dark matter that swaps hulking WIMP, weakly interacting massive particles, for ultralight, wave-like particles. Imagine dark matter not as discrete specks, but as a pervasive quantum fog vibrating at specific frequencies. In this model, filaments could arise from interference patterns in this fog, their density variations akin to standing waves in a vibrating string. Actions, if they exist, would be billions of times lighter than traditional dark matter candidates, behaving more like a fluid than individual particles. Supercomputer simulations show this. Fuzzy dark matter could naturally form filamentary structures while also solving small-scale puzzles, like why some dwarf galaxies appear smoother than standard dark matter models predict. Yet even these alternatives have gaps. Neither Mund nor actions cleanly explain all the cosmic web's observed features, like the precise temperatures of filament gas or the way galaxy clusters merge. That's why some researchers flirt with hybrid theories like emergent gravity, which suggests gravity itself arises from the universe's quantum entanglement structure. Others explore sterile neutrinos or primordial black holes as dark matter candidates, each offering subtly different blueprints for filament formation. The beauty of this debate, it forces us to question assumptions, whether filaments are woven by unseen particles, tweaked gravity, or something stranger. their existence reminds us that the universe still holds profound mysteries. Every telescope pointed at the cosmic web isn't just mapping structure, it's testing the very laws we thought we knew. When galaxy clusters collide along dark matter filaments, it's not a slow-motion fender bender, it's the universe's most extreme pileup. Picture two sprawling metropolises, each with thousands of galaxies, slamming into one another at millions of miles per hour. But here's the twist: the galaxies themselves barely notice. They're like cars zooming through fog so thin they pass right by each other. The real action happens in the space between them, where superheated gas, packed tighter than the filament's usual mist, gets crushed in a cosmic vise. The result: shockwaves rippling through the intergalactic medium, heating gas to temperatures hotter than the sun's core and sparking radio emissions bright enough to outshine entire galaxies. Take the famous Bullet Cluster. Here, two galaxy clusters plowed through each other, but their dark matter, detected via gravitational lensing, sailed ahead like phantom holes, barely interacting. Meanwhile, the cluster's visible gas collided so violently it created a bow shock visible in X-rays, a cosmic sonic boom frozen in space. The collision zone became a particle accelerator of unimaginable scale, flinging electrons to near-light speeds. As these electrons spiral through magnetic fields, they emit synchrotron radiation, long tendrils of radio waves that outline the wreckage like neon paint. Astronomers call these emissions radio relics, and they're some of the most dramatic road markers in the cosmic web. But the chaos doesn't stop there. Collisions along filaments can trigger chain reactions. Shockwaves reverberate down the filament's length, compressing gas and igniting new stars in galaxies caught in the turbulence. Some simulations suggest these pileups even twist magnetic fields into cosmic-scale ropes, channeling energy across millions of light-years. In the El Gordo cluster, for instance, a titanic merger generated radio relics stretching over 6 million light-years, evidence of shockwaves racing along filaments like tsunamis down a canyon. What's wild is how quiet this violence looks in visible light. Without radio and X-ray telescopes, we'd miss the spectacle entirely, galaxies drifting peacefully past one another while the space between them roils with invisible fury. These collisions aren't just cosmic accidents, they're transformative events. By studying them, we're decoding how filaments redistribute matter and energy, why some galaxies suddenly flare with new stars, and how the universe's largest structures evolve. Every merger is a live experiment, revealing the rules of a game where gravity writes the laws. Dark matter draws the board, and ordinary matter, caught in the middle, lights up the sky. Deep in an underground laboratory shielded from cosmic interference, scientists are preparing to hunt for ghosts that might reveal dark matter's hidden hand. The Ptolemy experiment, a next-generation neutrino detector, could soon uncover something revolutionary: the subtle fingerprints of cosmic filaments imprinted on the most elusive particles in existence. Neutrinos, often called ghost particles, pass through planets like they're not even there, rarely interacting with anything. Yet their paths might bend ever so slightly as they traverse the universe's vast filamentary web, warped by dark matter's gravitational tides. If we can catch that distortion, it would be like finding the shadow of an invisible giant. Ptolemy's approach is ingenious. By trapping ultra-heavy hydrogen isotopes on graphene sheets chilled to near absolute zero, the detector aims to capture the faintest neutrino interactions down to energies comparable to a single microwave photon. Why does this matter? Because neutrinos traveling through dense filaments should gain minuscule amounts of energy from dark matter's gravity, like hikers picking up speed as they descend a mountain. Spotting that energy shift could let us map filaments not by their light or X-rays, but by how they nudge particles that barely notice the rest of the universe exists. But the real breakthrough isn't just detection, it's precision. Previous neutrino observatories like IceCube or supercamioc and excel at catching high-energy neutrinos from cataclysms like supernova. Ptolemy targets the opposite end of the spectrum, relic neutrinos left over from the Big Bang which have been drifting through filaments for billions of years. These ancient particles could carry distortions accumulated over cosmic timescales, revealing how filaments have evolved since the universe's infancy. It's like analyzing the wear patterns on a river stone to reconstruct the currents that shaped it. The challenges are staggering. Not only must Ptolemy filter out Earth's constant neutrino background, trillions pass through your thumbnail every second, but it also needs to distinguish filament-induced shifts from other cosmic noise. That's where quantum tricks come in. The detector's graphene sheets are engineered to vibrate at specific frequencies, acting like tuning forks that resonate only with neutrinos influenced by dense gravitational fields. If it works, we'll have a new lens for observing the cosmic web, one that doesn't rely on light at all. What's thrilling is the potential for discovery. Neutrino mapping could reveal filaments too tenuous for current telescopes, or expose hidden branches in the web where dark matter's density fluctuates unexpectedly. Some theories even suggest filaments might concentrate certain neutrino flavors, creating faint currents in the particle flow. If so, Ptolemy could uncover not just where filaments are, but how they behave on quantum scales, blurring the line between cosmology and particle physics in ways we're only beginning to imagine. This isn't just about filling gaps in a map. It's about decoding gravity's subtlest language, written in particles that have witnessed the universe's entire history. Every neutrino deflection, every energy shift is a whisper from the dark, a clue to how the cosmos built itself from nothingness. And with detectors like Ptolemy coming online, we're closer than ever to hearing that whisper clearly. Human eyes scan the cosmos, but they're no match for the sheer vastness of the cosmic web, where filaments stretch so faint and diffuse they blur into the background noise of the universe. That's where artificial intelligence steps in, trained to spot the subtlest patterns in data that even the sharpest astronomers might overlook. Think of it like trying to trace a single thread in a tapestry from across a football field. Our brains aren't wired to catch those faint, sprawling structures, but neural networks thrive on the challenge. Take the Dark Energy Spectroscopic Instrument, or DESI, which maps millions of galaxies across 1/3 of the sky. The raw data is overwhelming billions of galactic positions, velocities, and redshifts, but AI acts as a cosmic cartographer, sifting through the noise to reconstruct the web's hidden scaffolding. One breakthrough came when researchers fed galaxy positions into a machine learning algorithm inspired by protein folding models. The result, a 3D map revealing filamentary connections so tenuous they'd been invisible to traditional statistical methods. It's like discovering an entire subway system beneath a city you thought you knew. The magic lies in how these algorithms learn. Instead of being told what to look for, they're trained on simulated universes, digital playgrounds where dark matter filaments form under known physics. By analyzing countless variations, the AI internalizes the subtle gravitational signatures of filaments, then applies that intuition to real telescope data. In one striking case, an AI trained this way pinpointed a filament between the Virgo and Coma clusters that human analysts had dismissed as random galactic scatter. Follow-up observations confirmed it a faint bridge of gas and galaxies, exactly where the machine predicted. But AI's real power isn't just finding known structures, it's revealing new ones. When researchers at the Flatiron Institute applied deep learning to Sloan Digital Sky Survey data, the algorithm flagged unusual filamentary arcs near galaxy voids. These weren't the straight, dense threads expected. They were warped and knotted like cosmic spaghetti stirred by unseen forces. Theorists now suspect these kinks could be relics of ancient collisions between superclusters frozen in time. Without AI's pattern recognition, we might have ignored them as cosmic static. The future gets even wilder. Projects like Euclid and the Vera Rubin Observatory are generating petabytes of data, far too much for humans to process alone. AI doesn't just help, it's becoming essential, evolving from a tool to a collaborator. Some teams are even experimenting with generative models that predict where filaments should be based on sparse inputs, like sketching the rest of a mural from a single brushstroke. Yet for all its brilliance, AI still needs human guidance. The cosmic web isn't just math, it's a story of gravity, gas, and galaxy evolution. Machines find the threads, but scientists interpret their meaning. Together, they're weaving a new understanding of the universe, one invisible filament at a time. Buried within the cosmic web's filaments lies a time capsule, an archive of the universe's infancy written in the language of gravity and gas. These sprawling threads aren't just highways for galaxies, they're relics of the cosmos's most dramatic growth spurt, preserving faint echoes of the density fluctuations that emerged mere moments after the Big Bang. To trace these clues, scientists have become intergalactic archaeologists, sifting through the web's structure like detectives examining fossilized footprints. The deeper they dig, the clearer it becomes. Filaments are the universe's original blueprints, frozen in time. Consider the universe's first billion years. Before stars or galaxies existed, dark matter's tendrils began forming in regions where quantum fluctuations had left space slightly denser. As gravity amplified these wrinkles, they grew into the filaments we see today, but crucially, their initial shapes weren't random. They carried imprints of those early quantum ripples, like stretch marks on expanding fabric. By measuring how filaments branch and curve in modern sky surveys, researchers can reverse engineer their primordial origins. The most telling details: filament junctions where multiple strands converge. These nodes often host the universe's oldest galaxies, acting as cosmic timestamps that reveal when and how matter first pooled together. One striking example lies in the Sloan Great Wall, a filamentary structure so ancient it's practically a fossil itself. Here, galaxies are arranged in a pattern that matches simulations of the universe at just 2 billion years old, a snapshot of adolescence preserved in the web's geometry. Even more revealing are void filaments, the wispy threads stretching across near-empty regions. Because voids experience less later-stage chaos from galaxy collisions and star formation, their filaments remain pristine, like undisturbed sediment layers in a geological dig. By comparing these untouched threads to denser cluster filaments, astronomers isolate how gravity and time have warped the universe's original scaffolding. The tools of this trade go beyond telescopes. Cosmologists run numerical experiments, simulating thousands of universes with slightly tweaked initial conditions to see which ones grow structures matching our observed web. It's like replaying a cosmic tape recorder, adjusting the static until the song sounds right. The simulations that best replicate today's filaments all share one feature. They start with quantum fluctuations of a very specific magnitude, the exact pattern detected in the cosmic microwave background. This consistency is the smoking gun, proving filaments didn't emerge randomly but were encoded into the universe's DNA from the very first moments. Perhaps the most startling insight comes from studying filament temperatures. The hottest gas filaments detected through X-rays often trace the web's oldest, most established routes, like well-worn trade paths in an ancient civilization. Their heat isn't just from recent activity. It's accumulated over billions of years as gas sloshed along the same gravitational channels, compressing and heating with each cosmic epoch. Meanwhile, cooler filaments spotted through subtle hydrogen absorption lines act as cosmic ice cores, preserving the chemical composition of the early universe. Some even contain pockets of nearly pristine gas, untouched by star-forged metals, offering a taste of the universe before pollution. What's emerging is a radical new way to study cosmic history. Instead of relying solely on distant light from ancient galaxies, light that's stretched and dimmed by expansion, we can read the web's structure like tree rings. The spacing between filaments encodes the universe's expansion rate. Their thickness reveals how quickly dark matter clumped. their gas chemistry tells the story of the first stars. It's all there, waiting in the threads we once thought were mere scaffolding. The cosmic web isn't just holding the universe together, it's keeping its memories alive. What if our cosmic web isn't unique? Just one thread in an infinite tapestry of universes, each with its own invisible architecture. The idea of a multiverse isn't just science fiction. Some of physics' most ambitious theories suggest our universe might be one of many, bubbling up from a deeper cosmic froth. And if that's true, dark matter filaments could take on forms beyond anything we've imagined, structures so alien they'd rewrite the rules of reality itself. Picture a universe where dark matter isn't cold and ghostly, but sticky and clumpy, binding galaxies into dense knots instead of wispy threads. Or one where filaments aren't straight highways but spiraling whirlpools, twisting galaxies into fractal whirlwinds. In a multiverse, the constants of physics, gravity's strength, dark matter's properties might vary from universe to universe. Some could have filaments so dense they collapse into black hole strings, while others might be so diffuse that galaxies drift apart like smoke in the wind. The cosmic web, we know, relies on a delicate balance. If dark matter interacted even slightly more, filaments might crumple into sheets. If it interacted less, they'd never form at all. Consider string theory's vision of the multiverse, where higher dimensional brains collide, birthing universes with entirely different physical laws. In one of these sibling universes, dark matter might be charged, weaving filaments that glow with dark electromagnetic storms. In another, filaments could pulse like living veins, expanding and contracting with cycles of cosmic respiration. There's even a wild possibility that some universes lack dark matter entirely, their galaxies held together by modified gravity or some other force we've yet to conceive. The most tantalizing clue might come from cosmic microwave background anomalies, those faint, unexplained patterns in the afterglow of the Big Bang. Some theorists speculate they're scars from collisions with other universes, where their dark matter webs briefly brushed against ours. If true, those scars could hint at filaments in universes next door, their structures imprinted like shadows on our sky. Of course, this is all speculation dancing on the edge of science. But that's the thrill of the multiverse idea. It turns the cosmos into a laboratory of infinite possibilities, where dark matter's role isn't fixed but fluid. Whether these alternate webs exist or not, the thought experiment alone stretches our understanding of what filaments could be. After all, if our universe's structure emerged from simple rules and random quantum seeds, who's to say those rules can't spin wildly different tapestries elsewhere? The cosmic web we see might just be one variation on a theme, played on a keyboard with infinite keys. Our Milky Way isn't some lonely island drifting through the void. It's a hitchhiker on the cosmic web's grand superhighway, surfing a dark matter filament through the universe at over 2 million kilometers per hour. Picture this: we're perched on one of Laniakea supercluster's many tendrils, a ribbon of invisible matter guiding not just our galaxy, but thousands of others in a slow gravitational ballet. Laniakea, Hawaiian for immeasurable heaven, is an apt name for this sprawling metropolis of galaxies spanning 500 million light-years, with the great attractor at its heart like a gravitational beacon. And right now, our galactic neighborhood, the Milky Way, Andromeda, and dozens of smaller galaxies, are all sliding along this filament toward that mysterious focal point, like leaves caught in a cosmic river. What's wild is how ordinary our place in this web actually is. The Milky Way's filament isn't one of the universe's thickest or most bustling. It's more like a suburban avenue compared to the dense intergalactic freeways near galaxy clusters. Yet even this modest thread has shaped our galaxy's destiny. Studies of nearby dwarf galaxies reveal they're not randomly scattered. They cluster along the filament spine, trailing behind us like ducklings in a row. This isn't coincidence, it's dark matter's gravity sculpting the local cosmos, herding galaxies into orderly lanes over billions of years. Zoom out further and the sheer scale of our trajectory humbles. The filament we're riding is part of a larger flow, a convergence of galactic currents all streaming toward the Norma cluster near the Great Attractor. But here's the twist: we'll never reach it. The expansion of the universe is stretching space faster than we're moving, leaving us forever paddling upstream in a river flowing the wrong way. It's like running on a treadmill that's speeding up. No matter how fast we go, the finish line recedes. Yet this cosmic commute isn't futile. The filament's gentle tug has already altered our galaxy's history. Gas streaming along this dark matter highway likely fueled star-forming bursts in the Milky Way's past, and today, it's still delivering fresh material from the local group's sparse surroundings. Even our galaxy's famous spiral arms might owe their symmetry to the filament's steadying influence, a counterbalance to the chaotic pulls of nearby galaxies. But the real wonder isn't just where we're going, it's what we're leaving behind. As we glide through the web, the Milky Way sheds its own gravitational wake, a faint ripple of distorted space that tugs on galaxies trailing in our path. Future civilizations in those galaxies might one day look back and see us as part of the filament structure, a knot in the cosmic net that helped steer their own journey. That's the irony of our place in the web. We're passengers and participants shaped by dark matter's currents even as we reshape them for others. So next time you gaze at the night sky, remember, you're not just looking up. You're looking along the grain of the universe, peering down the very filament that's carried us across cosmic time. And somewhere in the darkness ahead, the web's next great junction awaits, where new galactic encounters will unfold on scales we're only beginning to imagine. 1 trillion years from now, the cosmic web we know, those luminous threads knitting galaxies together, might resemble a tattered tapestry slowly unraveling in the wind. As dark energy accelerates the universe's expansion, filaments face a paradoxical fate. Stretched so thin they cease to function as cosmic scaffolding, their gravitational grip overcome by the relentless push of empty space. Picture a spider's silk filament pulled taut until it vanishes into nothingness, not with a snap, but with a whisper. Galaxies once tethered to these highways will drift apart like ships losing sight of one another in an ever-widening ocean, their shared velocities no longer enough to bridge the growing voids between them. But this dissolution won't happen uniformly. The universe's thickest filaments, those superhighways feeding galaxy clusters, will cling to structure longest. Their gravitational wells run deep, anchoring galaxies in place even as space expands. Yet over time, even these titans will fray. Simulations suggest that in 100 billion years, the edges of filaments will begin to evaporate, their outermost galaxies slipping away first. Star-forming gas, once channeled so efficiently along these routes, will diffuse into the void, leaving behind galactic ghost towns, clusters still bound by gravity but cut off from the web's nourishing currents. The universe's grand metropolises will become isolated islands, their lights fading as fuel runs out and stars burn through their final reserves. Dark energy's role in this unraveling is peculiarly cruel. Unlike gravity, which weakens with distance, dark energy's repulsive force grows stronger as space expands, creating a feedback loop of acceleration. Filaments won't just stretch, they'll be stripped, their matter diluted until gravity can no longer pull it back. Imagine baking a loaf of bread laced with elastic threads. At first, the gluten holds everything together, but as the dough rises, those strands thin and snap, leaving behind hollow pockets. The cosmic web will suffer a similar fate, its structure eaten away from within by the very fabric of spacetime. Yet there's a stranger possibility. Some theories suggest that in the far future, dark energy's dominance could trigger phantom energy, a scenario where expansion accelerates so violently that it tears apart not just filaments but atoms themselves. In this Big Rip scenario, even the fabric of spacetime could fracture, severing the universe's underlying connections in a catastrophic finale. filaments wouldn't just dissolve, they'd be annihilated, their gravitational bonds shredded in an instant. It's a far darker ending than mere dissipation, one where the universe's architecture isn't gently erased but violently erased. But perhaps the most haunting vision comes from the far quieter heat-death scenario, where expansion doesn't rip the web apart but leaves it frozen in place, preserved like a fly in amber. As the universe approaches absolute zero, filaments would linger as fossilized relics, their galaxies long since burned out, their gas too diffused to ignite new stars. The web would still exist in outline, a shadow of its former self, drained of all vitality. Future civilizations, if any could survive in such a bleak era, might gaze upon these structures and wonder at their purpose, like archaeologists puzzling over the ruins of a forgotten civilization. What's certain is this: the cosmic web's demise won't be a single event, but a slow fade, a series of quiet goodbyes as the universe's lights dim one by one. The same filaments that birthed galaxies will outlive them, their dark matter threads lingering even as the stars they nurtured blink out of existence. And in that distant future, the universe's greatest irony will be laid bare, that the very forces which built its grandest structures are also destined to dismantle them, leaving behind only echoes of a web that once held everything together. Ever noticed how soap bubbles cluster together, their shimmering walls forming delicate intersections like a miniature cosmic web? That's not just a pretty accident, it's physics echoing across scales. You can recreate the universe's filamentary structure right at your kitchen sink. When soap films meet, they naturally arrange themselves into triangular junctions with thin strands of liquid stretching between them. These ephemeral threads mirror dark matter's gravitational pull, effortlessly channeling flow along invisible pathways. Blow gently on the bubbles and watch how the soapy filaments wobble but hold their shape, just like the universe's tenacious strands resisting cosmic expansion. For an even earthier analogy, look to dried mud. When parched soil cracks, it fractures into intricate networks of ridges, raised lines where material has gathered, separated by empty gaps. The pattern isn't random. As moisture evaporates, the contracting particles follow paths of least resistance, clustering along stress lines just as matter streams along dark matter's gravitational grooves. Zoom in on a mudflat surface and you'll see the same branching hierarchy found in supercomputer simulations of the cosmic web. Thick primary cracks, the universe's supercluster filaments splitting into finer tributaries, the local galactic threads. The cracks even curve around denser clumps of soil, mirroring how filaments bend near galaxy clusters. Here's a more tactile experiment. Stretch a nylon stocking over a bowl and sprinkle flour over it. The threads of the weave will catch the powder, creating a dust-filled grid with dense knots where the fibers intersect. Those flour-coated strands, they're your DIY dark matter filaments, funneling material toward intersections that mimic galaxy-rich nodes. Tap the bowl lightly, and you'll see the flour shift just as galaxies slide along cosmic filaments over eons. The stocking's elasticity even mirrors space-time's flexibility, warping under the flour's weight like gravity warps the fabric of the universe. Want to witness filament formation in real time? Try this. Mix cornstarch and water to create oobleck, that peculiar goo that acts like a liquid when poured but solid when punched. Pour it onto a flat surface and slowly pull the edges apart. As the oobleck stretches, fibrous strands emerge between separating blobs, resisting the pull until they finally snap. This tension between flow and structure is eerily similar to how dark matter filaments elongate as the universe expands, tenuously linking galaxy clusters across growing voids. The difference: in the cosmos, those threads never truly break. They thin and fade, their gravitational embrace persisting even as space stretches them to near invisibility. These kitchen experiments reveal a profound truth. The same physical principles shaping soap films and cracking mud also sculpt the universe. Patterns repeat because nature reuses its best solutions, whether she's building a bubble or a billion light-year filament. So next time you wash dishes or walk past a dried puddle, pause and look closer. You're not just seeing household quirks, you're glimpsing the universe's blueprints written in water, starch, and earth. From the faintest quantum whispers in the universe's first moments to the sprawling superhighways connecting galaxy clusters today, dark matter filaments have been the silent architects of reality. They're not just cosmic scaffolding, they're the glue holding everything together, the gravitational conductors orchestrating where galaxies form, how they move, and even how they'll collide in the distant future. Every star, every planet, every atom in your body exists because these invisible threads funneled matter into the right places at the right times. And yet, for all we've uncovered, the deepest mysteries remain. We still don't know what dark matter is, only what it does. We can't explain why filaments sometimes sizzle at millions of degrees or how their ghostly particles refuse to interact with anything but gravity. Each discovery peels back another layer, revealing new questions beneath. There's something humbling about realizing we're embedded in this vast web, surfing a filament toward an unseen gravitational attractor, part of a story written in dark matter's ink. It's a reminder that the cosmos isn't something out there, it's the fabric we're woven into, the stage and the script of our existence. Centuries from now, when astronomers map filaments we can't yet imagine or decode dark matter's true nature, they'll stand on the shoulders of today's explorers, those staring at distorted starlight, passing supercomputer simulations, and hunting ghostly particles in underground labs. So as we wrap up this cosmic journey, let's circle back to Carl Sagan's timeless words. The cosmos is within us, we are made of star stuff. But here's the twist, we're not just star stuff. We're the children of filaments, the offspring of a web that built galaxies before Earth even existed. Every time you look up at the night sky, remember, you're not just seeing distant lights. You're tracing the contours of the universe's hidden skeleton, glimpsing the architecture that made you possible. And somewhere in the darkness, the web's next great mystery waits, not just for telescopes or supercomputers, but for the curious minds ready to ask, what if? The cosmos is vast, but it's not indifferent, it's connected just like us.